Hello, everyone. I'm delighted to be the moderator for this session, the special sectional lecture on Beyond Linear Algebra. I'm Salil Vedant, a theoretical computer scientist at Harvard. And our speaker for this session is Bernd Sturmfels, who is a director at the Max Planck Institute for Mathematics and the Sciences in Leipzig, and a professor of mathematics, statistics, and computer science at UC Berkeley, and an honorary professor at the Technical University of Berlin and the University of Leipzig. Sturmfels works in combinatorics, commutative algebra, algebraic geometry, and applications to statistics, optimization, computational biology, and has received numerous awards, to name a few: Packard Fellowship, Clay Senior Scholarship, Humboldt Senior Research Prize, the von Neumann Lectureship, and the Birkhoff Prize. To not take any time away from the talk, I will hand it over to Bernd for the talk. If you have questions, please put them in the Discord in the channel for section 14, and I will monitor that. And if we have time at the end, I will read those questions aloud.
Yeah, thank you very much for the introduction. It's a great honor and pleasure to be here. Let's start with some linear algebra. So all undergraduate students of mathematics learn about Gaussian elimination, which is a general purpose method for solving linear systems of algebraic equations. So here we have a system of three linear equations and three unknowns, x, y, and z. And you see that the output of the calculation reveals the answer. Here there's one solution, and the size of the output is smaller than the input. Now, of course, studying and solving very large linear systems is central to applied mathematics and many fields of the sciences and engineering. Now, moving on to nonlinear equations, lucky undergraduate students, some of them, also learn about Grobner bases, which is likewise a general purpose method for solving nonlinear systems of algebraic equations. So here I have a simple nonlinear system, again in three unknowns, x, y, and z, and we compute a Grobner basis, and you see the output here is in triangularized form. The first equation is one equation of degree 12 in z. This has 12 complex roots z. The second equation, we're solving a quadratic for y given any value of z. So there are now 12 times 2 solutions. And finally, the last equation expresses x in terms of y and z. So we see that there are 24 solutions altogether. Now, you also see that the output of a Grobner basis computation can be much larger than the input, and that's in fact a feature and often a disadvantage. Now, in recent years, numerical homotopy methods have proved to be fast and reliable in solving larger systems of polynomial equations, but in applying these methods, it's very useful to know a priori how many complex solutions to expect. So here we could have multiplied the degrees of the input equations 2 times 3 times 4 and predicted that there are 24 solutions. A classical example nearly 2 centuries ago is the problem of finding all conics, plane curves of degree 2, all red plane conics that are tangent to 5 given blue conics in the plane. And the answer to this problem is there are 3,264. It's an important number that really launched the development of enumerative geometry and modern intersection theory. But nowadays we ask, how fast can we compute these conics? And using reliable numerical methods, for example, the implementation of homotopy continuation in the software Julia, this can now be done in well under a second. So the setting of nonlinearity is that many models in the sciences and engineering are solution sets of polynomial equations, and such a solution set is called an algebraic variety. So X is a subset of R to the n that is a zero set to a finite list of polynomials in n variables. So here in blue, we see a surface given by the vanishing of one polynomial of degree 4 in 3 variables, n is equal to 3. The problem that will occupy us in the next half hour is to get close to the blue surface. So we have some data point that's outside we think about the blue surface as a model, a statistical or physical model, and we're trying to find the best or closest blue point relative to a given data point. So this is the problem of finding nearest points on varieties, and this will serve as my illustration for the appearance, importance, and solution of polynomial equations. So suppose we're given a variety x in R to the n, a real variety cut out by polynomials f1, f2 up to fk. I'm going to write ix for the ideal generated by these polynomials and c for the codimension of x. So the variety x has dimension n minus c. Now, an important quantity is the Jacobian matrix. So this is the k by n matrix, whose entry in row I in column j is the polynomial we obtain by taking the derivative of the ith polynomial with respect to the jth variable. And this matrix, for any point on the variety, has rank at most c. The rank is exactly c at points that are non-singular. There's a little bit of fine print here. We're going to assume that the non-singular real points are ample enough that they are dense in the variety in the Zariski sense. So then here in red, our optimization problem, given a data point u in R to the n, compute the distance to the model. Or more precisely, we seek a point, often the unique point x star in big X, that is closest to the data point u. Now, of course, the answer and the method of finding the solution will depend on the metric. And the simplest metric to take, already seen in the previous talk in this session, is the Euclidean distance, or rather the squared Euclidean distance. So the blue problem is to minimize the squared Euclidean distance subject to little x being any point in the variety, given the point u outside. So we would like to solve this exactly, reliably, by finding all local minima and, in fact, all critical points. So to quantify this, we're going to introduce an algebraic complexity measure called the Euclidean distance degree. So to compute this, we're going to augment the Jacobian matrix with an additional row. So we had the k by n Jacobian matrix, and we're adding an extra row on top of it with coordinates x1 minus u1, x2 minus u2, all the way up to xn minus un. We then calculate the c+1 times c+1 minors of the extended Jacobian. We look at the ideal. To this ideal, we add the given ideal, the given equations that cut out the variety. And then finally, to get rid of possible contributions from singular points, we are performing ideal saturation by the c plus c minors of the original Jacobian. The resulting ideal is called the critical ideal. So this is an ideal in the polynomial ring in n variables, x1 up to xn, that depends on the variety and the data point. Now the solutions, the zeros of the critical ideal, are exactly the critical points of our Euclidean distance problem. Turns out for a general data vector u, or general point u in R to the n, this set of critical points is a finite set, and it contains the optimal solution x star, provided the optimum is attained at a non-singular point. Then we define the ED degree, or Euclidean distance degree, to be the number of complex critical points. That is to say, the number of complex zeros of the critical ideal. This, as I said, is an algebraic complexity measure for representing the solution to the Euclidean distance problem. So this was introduced in a paper by Dreismer and collaborators about 6 years ago. Another way to say this is, suppose you compute the optimal point x star by any method whatsoever, and suppose you numerically represent the coordinates of this point x star, then these points, these coordinates, are algebraic numbers And this Euclidean distance degree is the algebraic degree of those coordinates. That is the degree of the lowest degree polynomial in one variable with integer coefficients that has these coordinates as a root. Now, to get a first sense of how big the ED degree is, here's a proposition. So suppose the given polynomials f1 up to fk that cut out our variety have degrees d1, d2 up to dk, ordered weakly decreasing. Then the Euclidean distance degree is bounded above by the product of two numbers. First, there's the degree of the first C polynomial, so the C codimension many largest degrees, d1 times d2 up to dc, times a second contribution that comes from the matrix, the Jacobian matrix. So it's the sum over non-negative integer vectors, I1, I2 up to IC, bounded by n minus c of this product, dj minus 1 to the power ij. Let's look at an example. Let's look at the case where k is 1, c is 1, and n is 2, and d1 is 4. So we have one equation in two variables of degree 4. So x is a quartic curve in R2. In this case, the sum, this product, becomes 16. Euclidean distance degree is 16. And for illustration, here is an explicit polynomial in two variables of degree 4, two variables x and y, and the zero set of this polynomial is called the trot curve. The real picture of this curve, shown twice, has four connected components, these bean-shaped ovals, and this, you see, the polynomial is symmetric, so the curve is symmetric. Now, not all of the critical points are real. 16 is the number of complex critical points. So let's say I take my data point, the blue point right in the middle, the origin. Then for that choice of data point, there are 8 real critical points. We see 4 local minima to Euclidean distance in green. We see 4 local maxima in magenta. So there are 8 real critical points, and then there are 8 more with imaginary coordinates. Now let's move the data vector to the right, inside the rightmost oval, and a little bit above the x-axis. Now there are 10 real critical points. There are 5 green local minima, and there are 5 magenta local maxima. And this 10 for this curve is actually the largest number of real critical points. So there are always some of these 16 critical points will be complex. Moving on to curves in three-dimensional space, let's suppose x is a curve that's defined by two general polynomials p and q in 3 variables, x, y, and z, where the degrees are d1 and d2. So in this case, the augmented Jacobian matrix is this 3 by 3 matrix. So the bottom 2 rows is just the Jacobian matrix. The top row is x minus u1, y minus u2, z minus u3. The critical ideal here, there's nothing to saturate because the polynomials are general. The critical ideal is generated by p, q, and the determinant of the augmented Jacobian. So this is a system of 3 equations and 3 unknowns, and the number of zeros is the product of their degrees. In red, that's d1 times d2 times d1 plus d2 minus 1. So this is the Euclidean distance degree. Now, if you think about this a little bit more geometrically, if x is any general smooth curve in any r to the n, the 2 basic invariants are the degree of the curve and the genus G as a Riemann surface, then the Euclidean distance degree is equal to 3d plus 2g minus 2. And we can check that the red formula works, is consistent with the blue general formula. So if we have a space curve, an intersection of 2 general surfaces, then the curve has degree d1 times d2. There's a degree genus formula given by this cubic expression in the lower right. And if you plug this into the blue formula, then you recover the red ED degree. I now like to state a first theorem, namely I like to state a general formula for the Euclidean distance degree for any real variety, x in R to the n, under some hypothesis, mild hypothesis, ... So if x is a variety that satisfies the ... hypothesis, then the Euclidean distance degree is equal to the sum of the so-called polar degrees of the corresponding projective variety. So we're going to look at the closure in complex projective space Pn. So we look at X as a complex projective variety. There are certain invariants to be defined in the next minute or two called polar degrees. And then we just add up these polar degrees, and that will be the red ED degree. Now, the hypothesis ... will hold for all varieties after a linear change of coordinates. So after you change the coordinates, you move the coordinates around, any variety will satisfy this. In special coordinates, it can fail. It has to do with tangencies to the absolute conic at infinity, but I'll sweep this under the rug. So X is any variety after performing a coordinate change, the conclusion of this theorem will be satisfied. So I need to define polar degrees. To define this, let's introduce the dual projective space. So we have the primal space that has points and hyperplanes, and they reverse their role in the dual space. They become now hyperplanes and points. So hyperplanes H in the primal space become points in the dual space. Now, taking a primal dual approach, let's consider pairs x, h, where x is a point in the primal space, h a hyperplane, such that x is a non-singular point in our variety and h is a hyperplane tangent to the variety at that point. Taking the closure of this collection of pairs defines the so-called co-normal variety n sub x that lies in the product space, the direct product of our two projective spaces, so point space and hyperplane space. Now, given the co-normal variety, we can define the dual variety x check. That's simply the projection of the co-normal variety into the second factor, into the space of hyperplanes. Now, here are three facts. If x is irreducible of whatever dimension, x is any irreducible variety whatsoever, then the co-normal variety will always be irreducible of dimension n minus 1. Right? So this is a general feature. So we're inside this ambient space of dimension 2n. The co-normal has dimension n minus 1. The co-normal is invariant under duality, and then taking the dual twice gets us to the primal back. Now, the polar degrees are the coefficients of the cohomology class of the co-normal variety. So the co-normal variety lives in this product of projective spaces. The integral cohomology is the polynomial ring in two variables, s and t, with integer coefficients truncated by modding out by s to the n plus 1 and t to the n plus 1. Now, since the co-normal has a dimension n minus 1, the cohomology class will be a binary form of degree n plus 1, homogeneous polynomial in S and T of that degree. The coefficients are non-negative integers, delta 1, delta 2, up to delta n. And the theorem is that you add up these deltas, and this will be the ED degree. Now, here is a geometric interpretation of these polar degrees, followed by another example. So classically, in geometry, the degree of a variety, say in projective space, is the number of intersection points with a general linear space of complementary dimension. Here, we're not in a projective space, but we're in a product of two projective spaces. So the role of a random linear space of complementary dimension will be played by a product of two linear spaces. The first space has dimension n plus 1 minus I in the point space. The second one, Li, has dimension I in the hyperplane space. Their product has dimension n+1. We intersect with the n-1 dimensional conormal variety. We get a finite number of points, and that number is the polar degree. So that's the geometric definition. Let's look at a surface of degree d in three-dimensional space. And let's calculate the d degree by this method. So in this case, nx is a surface, and p3 times p3. You simply attach to each point on the surface the tangent plane, right? That's a surface. It turns out that the cohomology class is d times d minus 1 squared. That's the degree of the dual surface. There's an intermediate term, d times d minus 1. And finally, the last coefficient d is the degree of the original surface. So adding up these three coefficients, we find that the Euclidean distance degree is d cubed minus d squared plus d. The two pictures are the same picture for d equals 3, right? So for d equals 3, on the right, we have a picture of a cubic surface with its 27 lines. But polynomials, homogeneous polynomials, can also be interpreted as symmetric tensors. So on the left, a cartoon of a symmetric 4x4x4 tensor, and that is the same data as a cubic surface. And the algebraic complexity of getting close to such a surface is d cubed minus d squared plus d, when the d is equal to 3 in this example. Now let's change the metric a little bit. And one other metric I like to mention, or class of metrics, is polyhedral norms. Polyhedral norms come up in many contexts, in particular in optimal transport. So the Wasserstein distance leads to polyhedral norms. And in this cartoon, I'm showing this for the L infinity norm. So for the L infinity norm, the unit ball is the unit cube. So in this picture, the ball is the cube, and the variety x is this sphere that's large and in green. The little green dot is the data point, right? So we're trying to measure the distance from the little green dot to the big green surface in the polyhedral norm, whose unit ball is the shown cube, the shown polytope. Well, how do you do this geometrically? Well, you place a small unit ball, that is to say a small cube, around the data point, and then you scale it until the cube hits the green model for the first time. Now, there are three different scenarios that could happen, right? Either the touching occurs at a facet, or at a vertex, or at an edge. And we need to distinguish these three. So let's suppose in general that the optimal face of the unit ball has codimension I. So in the cartoon, I would be 0 on the left, I equals 2, I equals 1 on the left, I equals 3 in the middle, and I equals 2 on the right. Then analyzing these cases separately for each I, we have the following proposition. The polar degree, delta I, of the green variety is the number of critical points of the optimization problem of maximizing or minimizing a linear form on the intersection of X with a general affine space L of codimension I minus 1. So this is the formal way of saying this. So you can think about the proposition this way. So if you did not yet know what the definition of polar degree is, maybe the previous three slides were too fast, then you can use this proposition as a definition of polar degree. If you do know what polar degree is, then this proposition is a proposition. So this is the analysis for polyhedral norms, such as those arising in optimal transport. Now, a third scenario that I like to discuss is measuring the distance in the statistical sense of maximum likelihood estimation. So this is equivalent to Kullback-Leibler distance, but I will describe it in terms of maximum likelihood. I'm going to start with discrete statistical models. So statistical model, by definition, is a family of probability distributions. And here we're looking at probability distributions on a finite state space with n+1 states, which I call 0, 1, 2, up to n. The set of all probability distributions is the simplex of dimension delta n. I'm going to use the open simplex. So these are real vectors p with positive coordinates that sum to 1. Statistical model is any subset X of that simplex. But again, we will typically assume that X has a nonlinear algebraic representation. So X is a variety restricted to this simplex. The data now is typically an integer vector u, a non-negative integer vector whose ith coordinate ui is the number of observations that are in state I, the number of times you observe the state I by carrying out a bunch of experiments. Given that fixed data vector, the log likelihood function maps a distribution P to the sum of ui times log pi that is well defined because pi is a positive number. And the goal of maximum likelihood estimation is to maximize this function. So we'd like to maximize the likelihood function subject to all distributions P that happen to be in our model. So now we have this model, this green picture inside the simplex. Now, for example, if n is 3, so we have a tetrahedron and x is a curve in the tetrahedron, turns out that the ML degree, the number of critical points, is d1 times d2 times d1 plus d2 plus 1. So this is very similar in this example to the ED degree. In the ED degree, the last plus was a minus, and here is a plus. A cartoon of this situation from the book Algebraic Statistics for Computational Biology. So think about n as very large. So we have a very high dimensional probability simplex here indicated by this triangle. We have a very low dimensional red model X. This is this little red curve down here. The data vector is the empirical distribution. It's a rational point in the simplex. And we're trying to find the best blue point, p hat, in the model relative to the data. So this is kind of the closest point, but now not the closest point in the Euclidean sense, but in the likelihood sense. Often in applications, these models arise as the image of some parameterization f. So this parameterization ideally is a one-to-one or locally one-to-one. That is to say, the model is identifiable or locally identifiable. And one often asks not for the maximum likelihood distribution p hat, but for the maximum likelihood parameters theta hat. Now, I'd like to state a theorem that gives a formula for the maximum likelihood degree. Recall, the reason we want to calculate these degrees a priori is because this information, knowing the degree a priori, helps us a lot in reliably computing all the critical points and hence all local and global solutions using numerical methods. So to describe this, now we're going to view the model X in the complex projective space, p to the n, as before. So X, which was inside the simplex, the complexification of the simplex is the projective space. So now X is a projective variety. X naught is obtained from this variety by removing n plus 2 distinguished hyperplanes. First of all, there are the n plus 1 coordinate hyperplanes, p0, p1 up to pn. But finally, there's one more important hyperplane, the sum of the pi, that comes from statistics, right? That corresponds to the hyperplane at infinity, the sum of pi being 1 in the application. So this complement is an open variety. It's a so-called very affine variety. And the theorem states that the following: suppose this very affine variety is non-singular. So this variety is smooth outside the n plus 2 distinguished hyperplanes. Then the ML degree of our model is equal to the absolute value of the Euler characteristic of this manifold. So this is the topological Euler characteristic of this complex n-dimensional or real 2n-dimensional manifold X open. So in red, the role that polar degrees played for Euclidean distance is now played by the Euler characteristic for in the maximum likelihood setting. So both cases, there's sort of a numerative geometry quantity, and here it has a more of a topological flavor. Now, one person who made fundamental contributions to the topology and the connection between algebraic statistics and topology is Juni He. So Juni He won one of the Fields medals a few days ago, but not many people know that in addition to his amazing work on the algebraic geometry of matroids, he also wrote 3 very important papers on algebraic statistics. In one of them, he characterizes models of ML degree 1. Namely, a model X has ML degree 1. That is to say, the solution to the maximum likelihood problem is rationally expressible in the data. If that is so, then each coordinate is an alternating product of linear forms in the data with positive coefficients. So this was refined a little later, given a more real algebraic flavor in work with Duarte and Marigliano. But basically, this theorem is due to Juni He. I like to mention that these kind of algebraic statistical models come up in many contexts, and one that's been recently explored is the study of scattering amplitudes and scattering equations in particle physics. I'd like to very briefly describe the CEGM model for scattering. C is Cajazzo, Freddy Cajazzo, and his collaborators. And in geometric terms, this is simply the space of M labeled points in general position in a projective space of dimension k minus 1. General position means no k of them lie on a hyperplane. Now, formally, this can also be defined as a quotient of the Grassmannian. So we take the Grassmannian of k-dimensional vector subspaces in an m-dimensional vector space. That's a projective variety thanks to its Plücker embedding. By O, I mean I look at all those points, the open part where all m choose k Plücker coordinates are non-zero, and then I mod out by the natural m-dimensional torus action on this Grassmannian. So if k is 2, then this is the familiar moduli space M0M of m labeled points on the line, or m labeled points on the Riemann surface. Well, what I called data earlier is known as Mandelstam invariance among the physicists. So in physics, the coordinates of ui are called Mandelstam invariants. Now this, in fact, this open variety is a very affine variety, and we can choose the coordinates in the following elementary manner. So we represent a point in the Grassmannian as a linear space, as the row space of a k by m matrix. On the left k by k block, I have this funny antediagonal unit matrix. And then in the remaining k by m minus k matrix, I make one column, I scale one column, one row to 1, and the remaining xij are the coordinates. So we're very affine variety with those local coordinates. So we'd like to calculate the Euler characteristic of this open variety. And the reason we like to do this, because this is the ML degree. This is the number of critical points to the log likelihood function. This is the number of critical points to the scattering equations in the physics application. Here in this theorem, at the bottom, you see all the known numbers. So for k equals 2, the moduli space M0M is well known to have Euler characteristic m minus 3 factorial in red. But then these red, blue, and the magenta number, they are new and interesting. So for example, if you have 8 points in the projective plane, then the Euler characteristic is 188,112. This is the number of complex critical points for this optimization problem. And using the software I mentioned, the numerical homotopy method in Julia, or Bertini is another such system, we can compute in a reliable fashion all 188,000 solutions in a relatively short amount of time, maybe a couple minutes or half an hour. Now, they're not just discrete models in statistics, they're also continuous data. So the simplest, most well-known instance of continuous data are Gaussian distributions. So let me briefly talk about the analog, the likelihood geometry in the Gaussian case. So centered Gaussians are parametrized by their covariance matrix. So PD is the cone of n by n real symmetric positive definite matrices. A model family of distributions is given by a set X of such matrices, and the set for us will be a linear or nonlinear algebraic variety. The log likelihood function takes the following form. First of all, there is S, the sample covariance matrix. So now the data points are organized into the sample covariance matrix, again, an n by n symmetric matrix. And then we need to maximize the following function, log det of sigma inverse minus the trace inner product of S and sigma inverse. So sigma is the unknown covariance matrix, and it's invertible, and determinant is positive because it's positive definite. So sigma is the covariance matrix, sigma inverse is the concentration or precision matrix. Let's briefly discuss this in the linear case. So let's fix linear constraints on the concentration matrix. So we fix a linear space of symmetric matrices, LSSM, so linear constraints on the inverse covariance matrix. And in this case, the critical equations for our optimization problem have this following elegant formulation. So we're going to write K for the unknown concentration matrix, sigma for the unknown covariance matrix. Here, there are the bilinear equations that just say that one is the inverse of the other. Then here we have the linear constraints, K is an L on the concentration matrix. And finally, sigma, the covariance matrix, minus S, the sample covariance matrix has to be an L perp. Again, we have an ML degree, which is the intrinsic algebraic complexity of representing the optimal solution, every coordinate of the optimal solution using whatever method for computing, or equivalently, the number of complex critical points. So for example, if n is 4, so we have Gaussians in 4-dimensional space, and the model is a linear space whose dimension ranges between 1 and 10, say 2 to 9. Then the ML degrees are 3, 9, 17, 21, 21, 17, 9, 3. So we have a unimodal symmetric behavior. This can be explained by Schubert Calculus, and there is remarkable recent work by Mateusz Michalek and collaborators who says that the ML degree of L is the number of quadratic hypersurfaces, the number of quadrics in projective n-1 space that pass through a certain number of given red points, n plus 1 choose 2 minus k, and are tangent to k-1 general blue hyperplanes. They also showed that for fixed k, this number is a polynomial in n of degree k-1. So this solves a conjecture that arose in earlier work with Carolina Euler. So LSSM stands for linear spaces of symmetric matrices. This triangle of numbers, very nice log concave Lorentzian situation. The first row is our ML degrees, 1, 3, 9, 17, and so on. And otherwise, these numbers give us the number of solutions if we put 9 tangency constraints on an unknown quadratic surface in 3 space. Each tangency constraint is either containing a point, being tangent to a black line, or being tangent to a blue plane. So for example, in the middle, we have 104. This is the number of quadratic surfaces in blue that pass through 3 given red points, are tangent to 3 blue planes, and tangent to 3 black lines. I like to end in time, so only 3 more slides left. And I like to end by remarking that polynomials, so we discussed modeling with polynomials, we discussed solving polynomial equations, but I like to point out that polynomials are really the same thing as very special PDE. So a polynomial is exactly the same thing as a linear homogeneous partial differential equation with constant coefficients. So suppose we have this polynomial in 2 variables, x and t, x squared minus t squared, which factors happily. We can interpret this as a partial differential equation for an unknown function phi in a space variable x and a time variable t. Now, this is a very familiar differential equation. This is the one-dimensional wave equation. And even longer ago than our 3, 2, 6, 4, in 1747, D'Alembert showed that the general solution to this partial differential equation is the superposition of traveling waves. So the set of solutions is an infinite dimensional vector space, but this infinite dimensional vector space has a representation by 2 things, namely any function f of x plus t plus any function g of x minus t, where f and g are reasonable functions or in fact distributions. There's been a lot of recent work connecting polynomials and linear PDE, and we like to do this recent work for any ideal in a polynomial ring, in fact, any submodule over a polynomial ring. This point of view was dear to the heart of Wolfgang Gröbner. Gröbner bases were mentioned at the beginning, and in the 0-dimensional case, when our polynomials have finitely many solutions, the answer was very well known to Gröbner in the 1930s. So Gröbner in the 1930s wanted to lay the foundations of algebraic geometry using ideal theoretic methods, and he basically proved this theorem, which is theorem 327 in the Invitation to Nonlinear Algebra textbook that recently appeared. But in the general case, the situation is more subtle, but there's recent work that deals with this. We saw this picture on the first slide. It's Cayley's cubic surface. It's also the logo of the Nonlinear Algebra group of the Max Planck Institute in Leipzig. This picture represents statistics, right? So these are 3 by 3 covariance matrices with diagonals 1. This represents optimization, semi-definite programming, the so-called elliptope. But here in the context I alluded to in the last 2 minutes, this is actually PDE. This picture is a PDE. So if you look for an unknown function phi from R4 into C3, so it's the common setting in real analysis, we map from real to complex, then the 3 coordinates of this unknown function satisfy phi1, phi2, phi3 satisfy this matrix vector equation. So the first equation says that the derivative of phi1 with respect to x1 plus the derivative of phi2 with respect to x2 plus the derivative of phi3 with respect to x3 is 0. Now, Macaulay 2 is a symbolic Gröbner-based system for doing lots of calculations in algebraic geometry, and there's a recent command called solve PDE. So if you are a user of Macaulay 2, I'd like to encourage you to apply solve PDE to this matrix, that is to say, to this picture. Let me end by telling you why this was called Beyond Linear Algebra. So linear algebra is ubiquitous in the mathematical universe. The importance and value of linear algebra, nonlinear, numerical linear algebra can hardly be overestimated. Now, why is it so powerful? Is that because shapes are naturally linear? No, the power of linear algebra stems from calculus and our familiarity with calculus, our ability to approximate nonlinear blue shapes by linear spaces. The world, however, is nonlinear, and nonlinear polynomials of degree 2, 3 are a natural ingredient in mathematical world models for the real world. Now, of course, at the very end, we need to harness the power of numerical linear algebra. There's no doubt about this. But I like to posit that the nonlinear nature of a phenomenon model should be respected as long as possible. We advocate against the common practice in applied math of passing to a linear approximation right away. We should maintain nonlinearity and the methods of nonlinear algebra as long as possible before passing to linearization. Thank you very much for your attention.
Thank you for the fascinating talk. I'm afraid we don't have